happy that we have in our midst a person who's going to talk about that in depth. He is the director of the Alexander Grass Center for Bioengineering at the Hebrew University of Jerusalem, CSO of the Future Meat Technology Company, a biotech company developing a manufacturing technology that enables cost-efficient production of fat and muscle cells. Please give a big hand from Israel, Professor Yaakov Nahmias.
Thank you for the introduction, and thank you for the amazing Prof staff for putting together this amazing conference. So there are two dangerous things that you do. One is putting me on a stage with a microphone. There's a good chance I'll start singing. The second thing, actually, speaking right after Mark Post, who was a visionary, and some of the things that he did really took an amazing amount of courage. Now, it's not only taking your entire lab to convert it to make muscle, but actually putting it in front in live TV and having food critics eat the first burger without ketchup. Which is, and the fact that it got very stellar reviews tells you something about the potential of this field. But to start, I really want to take everybody a step back. Life on this planet wasn't as nicely conditioned as it is today. Our story really begins about 1 million years ago, with the first time that people on this frozen tundra, well, we call today Berlin, found fire and started eating meat. Meat, for us, since then, is a cornerstone of human culture and a significant part of our evolution. It's not only the protein content that allows us to make more and more humans, but also the fat content that allows us to build bigger and bigger brains, bigger than, but on ratio, all the other animals on the planet. We need that fat for our nervous system. This is why, meat is really revered today in every single culture on the planet, from Africa to Asia, from Europe to the United States. It's a centerpiece of the meal. We are looking for the protein, and we are revering it. There is a ceremony there. It's a centerpiece of every single holiday. This is why, in a Pro-Veg conference, as appealing as this is, and it is appealing, it doesn't give you the same emotional response as this. Now, take a second and take a deep breath. Look at the picture and take a deep breath. I don't care how long you've been a vegetarian. You can smell the meat roasting. And this is exactly the point. We have 1 million years of evolution ingraining neural circuits in our brain, demanding that we crave this. Now, you can replace this emotional response. And a lot of vegans and vegetarians, like my wife, for example, have replaced it with some sort of a distaste, but you can't be apathetic to meat. You either love it or you might hate it. But you can't be apathetic toward it because it generates an emotional response. Now, there's a lot of things we can do in the world today, especially in the last 5 years, and there are these amazing companies here in Europe and abroad to do amazing things for the texture of meat. We can take plant protein. First, it was soy and then wheat. But now today, pea and hopefully chickpeas and beans in the future, and make amazing texture and color. So here I'm showing Impossible Food, the Impossible Burger, and the Beyond Meat. And we can get that. And Oja in Europe did an amazing job at getting that, is doing an amazing job in getting the texture, and even some of the companies, the Pro-Veg incubator. Our problem is the aroma, and our problem is the flavor. Both of them are not coming from the protein content. They're not coming from the muscle. They're actually coming from the white stuff over here. Okay, so if you take a look at the steak, the muscle fibers that Professor Post spoke about are really the red fibers that you see here in the cross-section. But what gives you the taste, the flavor, is the connective tissue, the muscle, the fat content of the burger, that when it hits the grill, when it oxidates, give you these hundreds of polyaromatic hydrocarbons, which are very difficult to replace. And this is really what we crave. Now, when we're trying to essentially look at the advantages of cultured meat, one of the major advantages is actually replacing everything, not only the texture. So the question becomes, where can we get this source of aroma and flavor? So there are different approaches used by different companies. You can take primary cells, right, like Maximal is doing, for example, muscle cells or even adipocytes, and they have a limited capacity to expand. It's around between half a ton to 50 tons, depending how you count, okay? If you want to make an infinite amount, unless you want to take multiple biopsies from the same animal, you need to immortalize the cells. You need to expand indefinitely. So you really need to use some genetic modification, whether by small molecules, just like it was said before, might be carcinogenic, or by genetically modifying the cells. And the same is true for pluripotent stem cells. Pluripotent stem cells need to be made by one of those genetically modified approach. But there is another source of cells out there. And the happy thing is that fibroblasts in our bodies are connective tissue in most of the species that we know, and that includes chickens, cows, beef, and lamb, can actually go a process called spontaneous immortalization. Okay? They can expand indefinitely without being stimulated by small molecules or by genetic modification. And there are a couple of major advantages to using fibroblasts. One, they grow faster. So if a doubling time for a primary cell is about 40 hours, and for stem cells a little bit shorter, about 30 hours, the doubling time for fibroblasts is about 20 hours, which means it's as fast as CHO cells, which is the standard for biological manufacturing today. The second thing is that culture medium is very cheap. You see, it takes a lot of growth factors and nutrients to maintain a cells in a specific state. So adipocytes and muscle cells cost about $250 per liter. If you want to maintain stem cells in a pluripotent state, it's a lot more expensive. They're really unstable. So you're talking about $400 per liter of culture medium. That's the food that the cells eat. But fibroblasts, well, they grow even on random media, on almost everything. They are the connective tissue cells. Every time we cut ourselves, these are the cells that double themselves in hours to close the wound. And they grow on a very basic medium down to about $50 per liter today. And this is serum-free medium. The last thing, and probably the most important, is the maximal cell densities you can actually get from these processes. You see, to be efficient, you need to have a very high yield. If your cells stick to a surface, if your cells are contact dependent, and you have to grow them in hollow fibers or on cytodex beads, then the maximal cell density is going to be about 5 million cells per milliliter. That means only around 2 to 5% yield. If you're growing aggregates like stem cells, you can get all the way to 30 million cells per milliliter. But that's still only 10% conversion of media cost to mass. But with fibroblasts, we actually found a way to grow them as single-cell suspensions. That means you can actually use perfusion technology and get all the way up to about 140 and even higher cells per milliliter. That's a yield of about 50%, which is a lot higher than other cell types. Essentially, it's the same as CHO cells, which is the standard for biological manufacturing. The second thing you need to understand is that this is really the story of the medium and the food is the beginning and the end, the alpha and the omega of the story. Today, the best biological manufacturing technologies, steered bioreactors the size of this entire building, 25 tons, need 10 liters of medium for every kilogram of mass they use. okay? It's really inefficient process. It's better than tissue culture in the lab, but it's really an inefficient process. You can get at best, if your culture medium costs the industry standard, which is $20 per liter, we have to be realistic here, $200 per kilogram. Now, animals, on the other hand, don't need that much medium. You don't need 10 liters of plasma to grow a single kilogram of mass. Thank God. Otherwise, I would be a huge bulb here on this table with my 100 kilograms. For every kilogram of mass we are growing in a cow or a chicken, we only need half a cup of water, 0.1 liters. And the reason it's so efficient is because we have a liver and a kidneys that continuously remove the toxins from the system. So just like Professor Post said, our cells are growing in their own ammonia, not urine, ammonia. And this is highly toxic. And this is why they have to be diluted, but this system, the normal system, can actually actively remove it. So our technology and future meat technology is actually based on this active removal of ammonia and toxins, enabling us a progressive perfusion and fed batch cultures, which should be able to go all the way to about a 1-to-1 conversion. The nice thing about this system is you could also dramatically reduce the capex. Because these systems are self-contained, you can get down to a very easy manufacturing process. And this is really how ammonia stripping looks like. So when you spike ammonia in culture medium, you can see that most of the cells die, about 30% die in about 24 hours. But you can actively remove it without damaging cell viability, and you can see that after 3 days, the cells stay alive, even if you initially expose them to 10 millimolars of ammonia. Let me show you some data. In the 8 months since the company has been starting to work, we generated 5 different immortalized fibroblast lines for chickens, 2 from beef. Okay, now we're working on lamb as well. They look like this, and these are cells that can feed the entire world, and they haven't been genetically modified. No small molecules, no genetic modification. We can take these cells and induce them to make fat using small molecules that have been approved by the FDA for human consumption. What you see here is the nuclei in blue and the fat in green. So this is chicken fat, highly efficient chicken fat, growing in suspension. And this is what you can do with it. This is a chicken skewer that actually combines plant protein with chicken fat. You can do both muscle and fat, but really fat is where the story begins. You can actually see it sizzling. You can't hear it right now. It costs 30 euros to make 100 grams of this. And this is a direct comparison. You see 2 pieces. One of them is real chicken. The other one is the future of meat. Now let's talk in the last minute I have about manufacturing, because this is critically important. A 600-liter bioreactor means you can generate 300 kilograms of fat every 2 weeks. That's essentially 2,000 kilograms of a hybrid mass. Essentially, we can replace this with 4,000, it replaces 4,000 chickens every 2 weeks. Now, chickens take 6 weeks to grow. That means we're talking about replacing 12,000 chickens or 4,000 square meter barn. I forgot I'm not in the United States, so it's in feet. 4,000 square meter barn with a facility that is the size of 120 square meters, essentially the size of a relatively large apartment in Berlin. Okay? So it's efficient in the space, but one of the things that we have to take into account is that we're talking about replacing the food industry. 32 billion kilograms of volume needs to be replaced. That's how much we need to make every year. 32 billion liters. Now, here is the problem. The entire biological manufacturing sector, Merck, Roche, all the big pharma companies, up to date, have only 1 million liters of bioreactor volume. We need to make that and increase it by 32,000. So if you imagine mega factories outside Berlin making cultured meat, then you are living in a dystopia. This is why we are going to a distributive manufacturing model. And there are about 250,000 farms just in the United States, and many more in Germany, where we can actually have a production facility, a manly production facility, for cultured meat that actually looks a lot like a mini brewery. Do you know how to make beer? So you'll know how to make cultured meat. Thank you. I'm sorry.
Perfect. Thank you so much for this fascinating presentation, Yaakov. There's time for one question from the audience. Who? The first. Yes.
I was first.
Yeah, you're first. You're first. Daniel.
So my name is Daniel. I'm from Germany. I have just one question. Where do all the amino acids come from that you want to convert into meat?
So the amino acids are mainly coming from plant protein. And it's an interesting, right, so we are actually talking, our investors are Tyson Foods and Netto, so we're talking about the feed manufacturers as well. And this is an important discussion to be had, right? Because if you want to change the supply at the end, you have to change the entire chain along it, right? We would need maize, we would need wheat, we would need corn, we would need to make combinations of products to actually feed this. But that said, amino acids is a small story. The biggest question is, where is the glucose coming? And really, the glucose needs to come from corn, right? That's the easy thing. But amino acids are interesting, but amino acids can actually come from plants. It's just that some of the amino acids have to be carefully chosen, right?
A very fascinating discussion coming up, and I'm sure we'll continue that also during the break. One big last hand for Professor Yaakov Nahmias. Christine.